Welcome back, everyone. Let's take a moment to recap the critical section problem, a fundamental challenge in concurrent programming. So the critical section problem refers to the challenge in operating systems where multiple processes access shared resources and compete for their usage. The problem arises when the outcome of the execution depends on the order of access to these shared resources. Remember that to solve the critical section problem, certain requirements must be met. So mutual exclusion requires that only one process can access the critical section at any given time. This ensures that conflicting actions do not occur simultaneously. And progress requires that if no process is currently executing in its critical section and some processes wish to enter their critical sections, then only those processes that are not executing in their reminder section can participate in deciding which will enter next. And this decision cannot be postponed indefinitely. Lastly, bounded waiting requirement is about a limit on the number of times other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before the request is granted. So these requirements ensure that processes can access shared resources without conflicting with each other, and also race conditions are prevented. As we move into this topic, we will explore various solutions to this problem. Last week, we mentioned software solutions to critical section problem. And this week, our focus will be on hardware solutions. And we also mentioned more advanced synchronization mechanisms, such as mutex logs, semaphores, and monitors. These methods play an important role in ensuring synchronization and data consistency in multi-process environments. So let's begin this week's discussion. So traditionally, systems have employed various techniques to address the critical section problem. One such method involves utilizing hardware solutions. Utilizing hardware support specifically designed to handle critical section problem. So in uniprocessor systems, one approach was to disabling interrupts. By doing so, the currently running code could execute without interruption, ensuring that no other process could preempt its execution. When interrupts are disabled on a uniprocessor system, mutual exclusion is preserved. Let's look at this example code of process PI. So here the process PI repeatedly enters a loop. And within this loop, the process disables the interrupt, okay, to establish atomicity for its critical section. And this ensures that the critical section's execution cannot be interrupted by external events or other processes. The process executes its critical section, which contains the code that must be executed without an interrupt for maintaining data integrity. After exiting the critical section, the process must enable interrupts, okay, which allows the system to respond to external events and allow other process to execute. The process continues with its reminder section, performing non-critical task. So while disabling interrupts offers a simple solution, this approach has a significant drawback, especially in multiprocessor environments. Yeah, sorry. Disabling interrupts globally across all processors might seem effective in theory, but in practice, it introduces complications that impact system efficiency. First, disabling interrupts on a multiprocessor system can be time-consuming. Okay, and since the messages pass to all the processors, this message passing delays entry into each critical section, and system efficiency decreases. So it's actually inefficient. And also consider the effect on a system clock if the clock is kept updated by interrupts. So therefore, we try to explore alternative synchronization methods. So modern computing systems with multiprocessors have evolved to provide specialized non-interruptible hardware instructions, test and set, and compare and swap operations. So test and set operation involve modifying the content of a word. So this atomic action ensures that no other process can interfere during this operation. And compare and swap operation involves swapping two variables. This swap occurs in a single indivisible step to guarantee the integrity of a shared data. So this figure shows the definition of test and set instruction. Hence, the instruction is atomic if two test and set instructions are executed simultaneously on different CPUs. They will be executed sequentially in some arbitrary order. To achieve mutual exclusion using the test and set, we use a Boolean variable, lock, and it is declared and initialized to false. So the mutual exclusion logic is implemented as follows. The test and set function checks the lock variable. If lock is true, indicating another process is in the critical section, so the current process enters a busy wait loop, continuously checking lock until it becomes false. Once the process occurs the lock, when lock was initially false, it enters the critical section and executing the mutually exclusive code. And at the end, after completing the critical section, the process must release the lock by setting lock back to false. And this action allows other processes to enter the critical section. So the process then executes the reminder section, which contains non-critical code. As you can see, in while loop, this solution suffers from busy waiting. In this case, processes continuously check the lock status, and it actually wastes CPU cycles without doing nothing. And let's break down how this compare and swap instruction works. So this instruction is defined as follows. It is again atomic, meaning it is executed indivisibly. If the current value of the target variable matches the expected value, the target variable is updated to the new value and the original value is returned. To achieve mutual exclusion using compare and swap, a global variable lock is again declared, and this time it is initialized to 0. The mutual exclusion logic is implemented as follows. So the compare and swap function atomically checks the lock variable. If lock is 0, indicating no other process is in the critical section, the current process enters the critical section. If another process is in the critical section, the current process enters a busy wait loop, which in this loop, it continuously attempting to acquire the lock until it succeeds. So once the process acquires the lock, it enters the critical section and execute the mutually exclusive code. And you know that after completing the critical section, the process must release the lock by setting lock back to 0. This action allows other process to enter the critical section. So then the process executes the reminder section, which contains non-critical code. This loop continues indefinitely, ensuring that the process repeatedly attempts to enter critical section based on the status of the lock variable. Please note that, like the previous solution, this approach also suffers from busy waiting, making it inefficient in practical scenarios. To sum up, in computer systems, accessing a specific memory location typically excludes other access requests to the same location, and which way it ensures data consistency. However, it causes inefficiency as computer systems have evolved. To address this, designers introduced special machine instructions capable of performing two or more actions atomically, meaning these operations are indivisible and cannot be interleaved by processes or instructions. However, they are also inefficient since it cannot avoid busy waiting. So more advanced synchronization mechanisms such as semaphores or monitors are preferred to avoid busy waiting.